Okay guys, welcome back to Chino Math. Today we're going to be covering z-intervals, and this is for AP Stats. For z-intervals, the proper name that we use is a one proportion z-interval, or at least for this case. And so what we use one proportion z-intervals for is just creating intervals for estimating true proportions. So we learned in previous chapters how to take samples. So a lot of times we'll take a sample, like let's say we took a poll and we found that 144 people in our sample out of 330 voters said that they would vote yes for an upcoming school budget. So taking a sample here, we could find, we use p hat as our sample proportion, and this is our sample statistic, and this could give us a sample statistic, sample proportion of 0.4364. With an interval, we can use this calculation to actually estimate a range that we'll be able to find our true proportion in, or our true proportion of voters that will say yes. So as many of you stats students may be familiar with, the way Mr. Regalo likes to teach intervals is with an 8-step process. And so let's just construct a z-interval for this. And there's a few different things we need to establish first. So first, we're going to need a level of confidence. So for this, I'm going to be using a 95% confidence. And so a 95% confidence interval is going to give me a conclusion where I'll be 95% confident that my true proportion will be in the interval. And we'll get more into that later. So the first step of constructing our confidence interval is just going to be putting down our sample statistics. So step one, we have our p hat, it's going to be equal to 0.43, and q is equal to 0.5636, and quick math. And then we have n is our sample size, and that's going to be equal to 330. And our second step here is going to be our assumptions and conditions. So for z-interval, first one, we need a random assumption, which means that it's just that this is a random sample, and we can usually just assume randomness. And then we have independence. And this is, once again, typically just assumed, but it's often said in our problem that they took a random sample and then they're random independent samples, whatever. But the ones we actually need to do work, so we need to do sample size. We need to make sure that we can expect at least 10 successes and 10 failures. So our NP and our NQ are going to be greater than 10. So if we were showing this in this case, we would show that our N, which is 330, times our p hat there. Are equal to greater than 10. So with our success and failure conditions, we see that we obviously very greatly exceeded 10, and we could have done this before writing all this math out, but you just need to you do have to show. You have to show that it works. And our third step is our model. In this case, the model we're going to be using is a normal model. This is so hard, bro. Our third step here is going to be writing out our model, and we will be using a normal model with the mean of p hat and the standard error, standard deviation of the square root of p q over n. So our p hat was derived from our sample, it's our sample proportion, and then our standard deviation or standard error is square root of pq over n, and show y here. So we saw in the binomial models, in our binomial models we were able to have sigma, or a standard deviation of x, and that was equal to the square root of npq. In our proportions, we take our means and we divide by our sample size. So for our z-intervals, we're looking for standard error, and the standard error is, we find out by taking the standard deviation and dividing it by the sample, dividing it by our population, because we're looking for a standard deviation within a population. And if we, with a little mathematical rearrangement, we'll see that this is the square root of PQ over N. So now doing this calculation, we see that the square root PQ over N is equal to the square root of
9.009.
over 330. And this gives us what?
9.009.
You said that?
Yep.
Okay. So now we have our normal model centered at 0.436, and the standard error of 9.0091. So now our fourth step. So now our fourth step is going to be writing out our name, and so this is a one. I'm just going to write one prop for one proportion. Z interval. And our fifth step, we have our formula. So our normal model we saw was centered at our p hat 0.4364 with a standard error of 9.0091, which we calculated with the square root of PQ over N. So our formula here for our interval is going to be centered at p hat plus or minus our critical value multiplied by the standard error of x. I'm just going to throw that into parentheses. And so now our critical value here is what we mentioned earlier. We had a 95% or 95% confidence level. And so what our critical value is basically just like it's like our z-score that we're going to need to contain 95% of this normal curve within. So what I mean is, so this would be, let's say we have our, this would be a z-score of 0, and then 1, 2, 3 out here, -1, -2, -3. And within certain levels of z-scores, we have different areas under the curve. So for 95% confidence, we want 95% of this normal model here, to be contained within our two flags. And so the z-score we see, or the critical value for 95% confidence, is approximately 1.96. And so some other levels we use, we also might use a 90% confidence, and then also a 99% confidence. Some other common critical values we'll see is with a 99% confidence, we'll use 2.58. And for 90% confidence interval, we use 1.645. So now I want to show how I actually got to these critical values that I just wrote on the board. So you should be familiar with second distribution and using Normalcdf. And so Normalcdf, we're able to use a lower bound, let's say -1.5, and upper bound of 1.5. And this is from a z-score of -1.5 to a z-score of 1.5, so 1.5 standard deviations above and below the mean. And this gives us approximately 0.87, so about 87% of the area under the curve will be found within this bound. So now if we just use inverse norm, it's kind of like the opposite of what we just did. Instead of putting in bounds and getting an area, we're going to put an area and get bounds. So I have it use a center right now, and so if I put in an area of, let's say 0.9 for a 90% confidence interval, it should give us the z-scores of the bounds that we would use to get 90% of the area under the curve. And so if I just second distribution, go back to inverse norm, and we were using a 95% confidence interval, so I put 0.95% of the area, and the tail we want it to be center. And if we press paste on that, press enter, and it gives us -1.9599 and positive 1.9599. So just using 1.96, we see that with a critical value of 1.96 standard deviations, plus or minus 1.96 standard deviations, we'll get 95% of the area under the curve within our bounds. So back to our formula, we're going to have our p hat here, 0.4364, plus or minus our critical value, which is 1.96, times our standard error, which is 9.0091. Mark, is that right? Actually, what if you messed up the standard error? I have to go back. I hope not. You're good. So with our model, we have our normal model centered, or we have our bound centered at 0.4364, which is our p-hat, and then plus or minus our critical value times our standard error.
I have to do it.
Yeah, so, okay, so this is actually our step 6, and so now like, you can graphically show this. So I'm gonna draw my little normal model, and so I draw my normal model here, and we have it centered at 0.4364. And I'm gonna draw my flags, and so we have our 95% inside our shaded area here. Our next step here is just gonna be calculator work, so I'm gonna go to stat, test, and remember we are doing a 1 proportion z interval. Right here. And so our x, which we saw was a 144, so 144 voters said yes, out of a sample size of 330, and we're looking for a 95% confidence interval. So now it gives us these two bounds, and we'll go back to the board. So as you see here, we have a plus or minus, so working this out, we should get two values, and on our calculator, we see that we got 0.3829 and 0.4899. So now this brings us to our conclusion, and using a 95% confidence level, we can say now that we are 95% confident. 95% confident
that our true proportion of.
And then, so in many different problems, you're going to have a lot of different things here. So in this case, it'll be 95% confident that a true proportion of voters that would vote yes on the budget. And so I don't really want to write that out, but that's basically like our little frame. 95% confident that a true proportion of voters that'll say yes in the budget falls within 0.3829 and 0.4899. So this is our little sentence frame that Ms. Margall likes to use for the conclusion. But all you really have to do, you have to list what you're looking for, like exactly what the proportion of you're looking for of the population, and then list your bounds that we found in our calculator using our test. And that's how you construct a z-interval. Okay, so I want to revisit critical values. So we saw with a 90% confidence interval, we had a critical value of 1.645. For 95%, we use 1.96. And for 99%, we use 2.58. So what this really means is that we're called critical values, and we use this notation for them. And if you're aware, it's kind of similar to the z-score. So let's say z-score of some value x, it would be x minus the mean, x bar, over the standard deviation, so sigma. And all this is the difference between that value and the mean divided by the standard deviations. So I'm going to think of some random number, like 1.6. And so if we got 1.6, that means that it's 1.6 standard deviations over the mean, or greater than the mean. So positive is greater than the mean, and if it was negative 1.6, it would be under the mean, so it would be less than the mean. And so what we use these critical values for is to set up a sort of range. So if I go here, and put my flags for my confidence interval, let's say I'm using 95% again, negative 1.96, and this is 1.96. This is just standard deviations, meaning within 1.96 standard deviations of the mean, we're able to fill 95%. So 95% of the area under the curve will fall within -1, or will fall within 1.96 standard deviations of the mean. And if we're using a different confidence level, let's say I'm using 90% confidence, it's just going to be slightly smaller. We have our 90%, and instead our standard deviation here, or our z-score here, sorry, is going to be 1.645, negative 1.645, and positive 1.645. So once again, within 1.645 standard deviations of the mean, we're able to find 90% of the area under the curve. So for our confidence intervals, we say that we would be 90% confident that the true value falls within this range. Or here, we're 95% confident that our true value or our true proportion falls within this range. Okay, I'll stop there. So I just want to do an example of a quick z-interval on the homework. So here we have number 12, and it says the Spike Network commissioned a telephone poll of randomly sampled U.S. men. Of the 712 respondents who had children, 22% said yes to the question, "Are you a stay-at-home dad?" So the question just says construct a 95% confidence interval. So our first step is just going to be sample statistics. So we have n equals 712, and then we're given p hat, that was 0.22. So now our second step, we have assumptions and conditions. So we're going to assume, and I'm just going to write random, and assume independence. Okay, and then we have our NP is equal to greater than 10 and NQ. So using NP, we have 712 times 0.22, and then 712 is 0.786. Okay, so that's for our conditions here, and now we have a model. And so we're centered out of p hat, and then our square root of p hat, q hat over n. So it's a normal model. So we have a normal model centered at 0.22, and a standard error of 0.0155. And then right here we have our name, so A1. For step 4, we have our name, so it's a 1 proportion z interval. And so now for 5, we write out our formula, p hat plus or minus our critical value times our standard error. And so step 6, we're going to work that out, 0.22 plus or minus, and we're at a 95% confidence interval. So we know the critical value for 95% is just 1.96 times our standard error, which we found here, which is 0.0155. And now 7, I'm going to go ahead and draw out my normal model. It's 95% within these bounds. And now I run the test. So to run the test, I'm just going to go stat, test, alpha A. And so x is, well, x, I'm actually going to use, you're only given your p hat and your n. So if I put in those two, it's going to give me 156.64. But we can't have that in our test, so I'm going to go ahead and round up to 7. And out of 712, with the confidence level of 95%, calculate, and it's giving me my bounds. Now I have my bounds of 0.19005 and 0.25096. So for 8, I'm just going to write 95% confident that the true proportion of, and in this case it's stay-at-home dads, falls within this bound and this bound. And I don't think anyone wants me writing out that whole thing. It's not going to be, you're not going to be able to read it anyway. I mean, honestly. It's kind of pathetic, actually. This whole video, like, I don't know how any of you could read any of this, but yeah. Well, that's one problem. And I'm not going to do the one with z-tests. I'll cover that in a future video, and I'll do the homework from that night with z-tests, but yeah, that's about it. Thank you. Okay.